The claim is that the number 65, it's 41 in base 16, and in base 61, it's 14. Similarly, that 665 in base 166 is 41, in base 661, it's 14. And similarly, if you write that number but with n sixes, then in this base, it's 41, in that base, it's 14. So let's prove this claim. By the way, what that means is that 65 is 4 times 16 plus 1. So in base 16, the digits are 4 and 1. And in base 61, the digits are 1 and 4. So it's 1 times 61 plus 4. Similarly, for 665, it's 4 times 166 plus 1. And 1 times 661 plus 4, and so on. So we're going to prove this claim down here. So here is our theorem. And we are going to prove this equality over here using induction. So this is true for any n. So we're going to use induction for the proof. The base case of n equals 1, we've already seen it. It's true. So that's checked off. And now we're going to prove the next step. So typically the tricky part of an induction proof is the induction step. And this is the case here. So we're going to prove the induction step. We're going to prove that if we know it for n sixes, then we know it for n plus 1 sixes, okay? So we are assuming this equality here, and then we're going to prove it for n plus 1 sixes. So we start with the quantity with n plus 1 sixes, 4 times 1, 6 is 6, and so on. And the first thing, we're going to use the distributive law to take that 6 out of there. So it's going to be 4 times this without that 6, plus 4 times that 6 plus 1. Next, this has a factor of 10 that I'm going to take out. Factor that out, and then you see this quantity here is what appears here, at least in this part of the equation. So that much is this much minus 1. So I'm going to substitute this by this minus 1, and that's when I'm using the induction hypothesis. That's when I'm using that I know the result for n. Okay, so we have that equality here, and now just actually distribute again the 10. 10 times this is this. 10 times 3 is 30, 10, and then 4 times 6 is 24 plus 1. We have this. Now I want here, instead of ending in 10, I want it ending in 61, so I'm off by 51. So take 51 out of here, and I'm left with 4. So the equality holds with n plus 1 sixes over here. So we've proved that with n, knowing it for n, I know it for n plus 1. So I've proved the induction step, and therefore, by the principle of mathematical induction, the statement is true.